To the last four examples, but I remembered I made a mistake on example 3. I had 10 over 3 as C. It should have been 100. I dropped off a 0 when I was working out the problem, so hopefully you saw that. But example 3, the initial amount should have been 100 over 3, not 10 over 3. All right, 4 months after stopping advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000. If the sales follow the exponential pattern of decline, what will they be to the nearest unit after 2 months, after 2 more months? So again, we're going to use y equals CE to the KT power, same formula we've been using. And the difference is we got 0, at time 0, there was 100,000 units. And then it said 4 months after it stopped advertising. So at 4 months, there were 80,000 units. And then it says in 2 more months, how much will they have? So that's going to be at 6 months. We want to know how many units they're going to sell. So that's what the question's asking about. So again, we're going to plug in this 0 first, because when you put that in for your exponent, C is just going to be that 100,000. So we get y equals same way we did before, 100,000 e to the KT power. Then we can use this next number to plug in to get K. So we're going to stick 80,000, and it's going to erase the y. Stick 80,000 in for that. And we're going to divide by 100,000, so that's going to be 0.8 is going to equal e to the k, and the t is going to be this 4 here, so that's 4k, and we're going to natural log each side, so the natural log of 0.8 is going to equal, and then when you natural log e, that 4k comes out because the natural log and e cancel each other out, so we get the k is going to be the natural log of 0.8 divided by that 4. So there's our k. All right, so then we can use our equation, y equals 100,000, because that was the initial. E to the kt, well, k is natural log of 0.8 over 4. And t is our formula. So we want to find when t is 6. So we put 6 in here, and you would type that whole thing into your calculator, and that's going to be the number of units. Now it does say round to the nearest unit, so you wouldn't have decimal on that. But the formula is this problem right here, but this thing right there would stay a t, and that would be the formula you use for that one. Okay, we're going to go on to Newton's law of cooling. So Newton's law of cooling is how things in a room cool based on everything around it. So like a bowl of soup, coffee, something you cooked, a pizza coming out of the oven, all that kind of stuff. And it comes to this formula right here that the change in the temperature, and that dT means the temperature of the object. If you read right here, it says the temperature of the object. So if you took pizza out of the oven, that'd be the temperature of the object, is directly proportional to the difference in the temperature of the surrounding medium. All right, so what that means is basically room temperature. Okay, so TE, this thing right here, is the room temperature. And okay, so T sub 0 there, this thing is the beginning temperature of the object, but that's the temperature of the object at a given time. So we're going to leave that. That is going to be a deal that we leave a variable. Okay. Tell you what, this is a long, I think this is going to be a long problem here. So plug this stuff into the formula that we got right up here. So we got dt. Change in the temperature over time, little t, is going to equal, I'm going to go back up and look real quick, k. So that k stays as a constant. So we got some k, and then the temperature of the object coming out of you, and minus the room temperature. And if you look, it says we got a constant room temperature of 60 degrees here. So there's our formula. Okay, so we're going to separate this. So the capital T is going to go to the left side with the dt. So I'm going to divide over here by capital T minus 60. And then I'm going to multiply the dt over to the other side with the k. So that's going to give me dt, and then I'm going to integrate each side. So I'm going to integrate the left side. That's going to be the natural log of the absolute value of t minus 60. And over here, it's going to be some kt power. And then it's plus a c. So now I want to solve this for capital T. That's supposed to be an absolute value symbol there. So I have e over here, e over here. So that's going to be a capital T minus 60 is going to equal, again, this e becomes that e to the c, and that whole thing becomes this new c I just wrote in over here, e to the kt power. And that, I could go ahead and add that 60 over, but I'm just going to leave it right there for now. So it says, using a cooking thermometer, he determines the cake cools from 100 degrees to 90 degrees in 10 minutes. So when he pulls the object out at time 0, the cake's 100 degrees. And then 10 minutes later, the cake is 90 degrees. So we're going to use the 0, 100 to get that C is going to be 100 again. So I'm going to go ahead and stick that 100 in there. And now I'm going to use this 90 and 10 in order to find the K. So I'm going to put 90 over here because that's the new temperature. And that's 10 minutes later. So this is going to be 100 E to the 10K. Now I can find K. So over here I got 30. 90 minus 60 is 30. And when you divide 30 by 100, you get 0.3. So 0.3 is going to equal E to the 10K power. And you natural log each side. So the natural log of 0.3 is going to equal 10K. So K is going to equal natural log of 0.3, either times a 10th or just divided by 10. So there's my K. So we're going to plug that into this thing up here. So I'm going to erase this K right there. I'm going to move that T over, if I can get it to erase. Okay, so then I'm going to stick that natural log of 0.3 over 10. And I got my T over here for the time. So I'm going to erase the rest of this underneath here because this is my original formula. And I could have a hard time getting this thing to erase, sorry. Okay, there we go. So there's the formula. Now the thing says the icing that is used for the cake cannot be applied till the cake reaches 80 degrees. Okay, so what that means is we got to plug 80. We'll plug 80 in right here for that T because that's what we want the temperature of the cake to be. And now we got to solve that for t. So 80 minus 60 is 20, and you're going to divide by 100, so that's 0.2. It's going to equal e. And then I'm going to take that 1/10 up to the power of 0.3 t. So these cancel out. So t is going to equal 0.2 divided by 0.3 to the 1/10 power, and whatever that comes out right there, that's going to be the time it takes for that cake to cool down to 80 degrees. Okay, we got one more problem to do, and hopefully it's not too long, but ooh, it's got multiple parts here. Fish bowls are being introduced into a man-made, fish are being introduced into a man-made lake. The change in the rate of fish, so that's df dt. Okay, so we got df dt is directly proportional to 900 minus the fish. So the rate of change of the fish with respect to time is directly proportional, which means it's going to be k times 900 minus f, where t is in years. At t equals 0, there are 400 fish. So again, what we want to do is we want to, I'm going to write down that point, 0, 400. And then it says 3 years later, there are 600 fish. So when this is 3, there's going to be 600 fish. So the first thing I got to do is, again, solve this thing for d. I get df's on one side, dt's on the other. So again, I'm going to divide each side by the 900 minus f. Okay, and then I'm going to multiply my dt over to the other side. I'm going to integrate. So let's see. This is going to be dt, and then I got to integrate, and I got to come over here and integrate. So again, this is going to be the natural log of 900 minus f. Now we do have a little problem here because that was a minus f. So I should have let u equal that, which means du would have been a negative dt. So that means I need a negative over here, like that, because I had to create and destroy a negative to get that to work out right. So this is going to equal a negative kt plus some c. So again, I'm going to do e to this power and e to this power. So again, I'm going to have 900 minus f is going to equal some c again, because it was e to the c, that goes in front, times e to the negative kt power. So there's my problem. And when I plug in this 0, 400, that's going to give me that c is 400. So I'm going to erase this c again. I'm going to stick 400 in there, just like I showed you on the first several problems. So 400 goes in there. So this is kind of my formula, except I'm really supposed to solve for f. So if you solve for f, you would end up getting on the right side 900 minus 400 e to the negative kt power. But I'm just going to leave it there because I got to solve for k anyway. So I'm going to stick 600 in for f. It's going to equal 400 e to the negative 3k power. Now I can solve that for k. So let's see, 900 minus 600 is 300. Take 300 divided by 400, that's 0.75. And that's going to equal e to the negative 3k. So I'm going to natural log 0.75. And that's going to give me, natural log over here is going to give me negative 3k. So k is going to equal the natural log of 0.75 divided by 3. Negative 3, sorry. That's going to end up being a positive because the natural log of 0.75 is a negative divided by a negative, but that's my k. So my formula is going to be 900 minus f. If you want to put ft, you can. And that's going to equal 400 e, and then k is that negative 1/3 natural log of 0.75 times t. So there's your equation. Okay, so I don't want to erase all that. Okay, so anyway, I wish I had, I guess I'm going to have to erase because I don't have the benefit of being in my room where I can make stuff happen really fast. So I'm going to leave that formula where it is. And then what I have to do, is I have to take and plug in this 3 in for that T right there. And then you're going to, again, when you solve this for f of t, you're going to get 900 minus 400 e to the negative 1/3 natural log of 0.75. And again, this all is one thing, and then that times your t, which in this case is going to be 3. So you type that whole thing in your calculator, and that's going to be the answer for part B. And then this last thing says, what's the limit as f of t goes to infinity? Well, what that means is, what's the most amount of fish this pond can hold? And just to give you the shortcut method, this number right here is 900. So this thing right here is going to be 900 fish, because that's the limit as t goes to infinity. That's the most water or most fish that pond could hold. So I hope you have a good one, and that's the end of these notes.